My name is Michael Singh, and today I will be discussing the in vivo sequestration of innate small molecules to promote bone healing. For some background, as many as 10% of surgically treated fractures do not heal, a condition known as a non-union. This condition is brought about by a variety of factors, including initial loss of bone due to the injury itself, multiple surgical revisions resulting in impairment of vascularization, and the local immune competence and infection with bone-degenerating diseases. Thus, approaches that enable innate repair mechanisms hold great potential for tissue repair. A leading methodology in regenerative medicine is transplantation of tissue-specific cells to promote tissue repair. However, this approach is hindered by various challenges such as high costs, constraints associated with cell isolation and expansion, and limited in vivo engraftment of transplanted cells. Another common methodology consists of mobilizing native cells to promote the natural regenerative ability of the tissues. But this approach is limited as the function of endogenous cells is regulated by their microenvironment. Furthermore, chemical regulation of endogenous cells has proven to be more feasible and equally as powerful at promoting healing function. Which brings us to adenosine, a small extracellular signaling molecule naturally present following fracture and integral to the natural repair mechanism of the bone. However, the use of adenosine in bone tissue regeneration has thus far been limited by how rapidly it metabolizes and the risk of off-target effects due to its ubiquity in the body. Thus, a biomaterial-based approach that can localize the adenosine signaling is a promising alternative to circumvent these limitations. As such, a PBA functionalized polyethylene glycol network capable of sequestering adenosine strictly at the injury site to augment the endogenous cell function and lead to improved tissue repair is proposed. The biomaterial patch is composed of two main parts, a polyethylene glycol cross-linked gel and an interior coating of PBA. The PEG gel is a non-degradable polymer with a repeating unit structure of CH2CH2O. The presence of the CC backbone in the structure is primarily responsible for the polymer's non-degradability. Moreover, it is characterized by its high resistance to adhesion of cells and small molecules. This set of properties make PEG appropriate for the current approach. The choice of a polymer material makes the gel easier to produce at a low cost and provides the balance between rigidity and ductility necessary for a patch. Moreover, being non-degradable ensures a long lifetime for the patch that can safely encompass the early stages of a bone tissue repair. This property also reduces the risk of the patch becoming dislodged from degradation and floating freely inside the body. Additionally, the microporous scaffolded architecture of the gel allows for maximal incorporation with PBA and contact with the region of interest. Lastly, its resistance to molecular adhesion ensures that all interaction with the adenosine results solely from the PBA coating, thus promoting the specific host response desired. Similarly, it ensures that there are no off-target effects caused by the patch itself upon application at the injury site. The PBA coating is a polymer with a repeating unit structure of 3-acrylamido-phenylboronic acid, with the key structure being the boronic acid group. The high selectivity of this group for diol-containing compounds makes it excellent for this application as it readily forms a dynamic covalent complex of cyclid boronate ester with the cis-diol-bearing adenosine. Moreover, this reaction takes place at physiological pH, which lends further support to the use of this material for this application. The selectivity of the PBA also minimizes the risk of off-target host responses. Current standard therapies in the field of bone tissue repair include fracture fixations, autografts, allografts, and demineralized bone matrix, among many others. However, these treatments all carry the risk of inducing a biological or mechanical deficiency or a lack of vascularization, all of which can lead to non-union. Moreover, these invasive mechanical procedures do not take into account the body's native molecular healing pathways. These issues are all addressed by the patch, as cohorts treated in the current study with PBA or PBA with added oxygen showed a better healing outcome compared to those treated without PBA both in vitro and in vivo. This is evidenced by the radiographic data depicting a larger extent of callus maturation, endochondral calcification, and angiogenesis seen in PBA-treated subjects, suggesting that the biomaterial-mediated localization of adenosine promoted bone healing. Moreover, the adenosine levels receded to normal physiological levels as healing progressed, further supporting the safety of this application. The primary limitation of the study is that it does not take into account age and sex-dependent fracture healing responses to adenosine. Furthermore, it does not explore the potential impact of pre-existing bone degenerating conditions, such as osteoporosis, to the bone healing mechanism. However, these concerns are planned to be addressed in future work by the researchers of this study. Thank you.